So this is the application to the design of rule-based system. This is the same figure as the previous slides. We have environment and population, and in visual, here is a set of rules. That is a rule-based system. This idea can be used for the design of decision tree in this figure, and also can be used for the design of neural networks. In this case, the individual is a neural network. Also, this idea can be used for multi-objective optimization, as Gary explained. Here we have an initial population. Then, in this case, we have two objectives. One is complexity minimization. The other is error minimization. So this is a two objective program. And using these two objectives as an environment, a population can be moved towards the palette front. Finally, we may have obtained these neural networks. The same idea can be used for the design of decision trees and also rule-based system. This is a fuzzy rule-based system. We have a lot of fuzzy rule systems. Some are very simple, easy to understand, and some are very complicated, but high accuracy. And now I'd like to move to the parallel distributed implementation. The difficulty in evolutionary computation is computation load. Here we have a training data and population of rule-based systems. This slide, fitness evaluation, looks easy because the training data is not so large. However, this slide, training data is larger than the before, so the fitness evaluation needs a lot of time. So the computation load is a problem. This slide, training data is very large, so fitness evaluation needs a long time. So the difficulty in application to large data set is the computation load for fitness evaluation. So the main issue in this presentation is how to decrease the computation load. If we use standard non-parallel model, fitness evaluation is performed something like this. So we need a lot of time. One idea is parallel computation. We can perform fitness evaluation for several individuals in parallel. If we use n CPUs for parallel computation, the computation load for each CPU can be 1 over n in comparison with the case of a single CPU. For example, in this slide, the computation load of each CPU is 25% of the original use. And another idea is training data reduction. The idea is very simple. Even when the data is very large, we can use only a part of them. Then we can decrease the computation load. So if we use X% of the training data, the computation load can be reduced to X% in comparison with the use of the all training data. So the fitness evaluation is performed like this. Only this part is used for fitness evaluation. But the problem is how to choose a training data subset. If we use only this part of training data set, the population will overfit to the selected training data subset. This is a big problem. For handling this difficulty, an idea of windowing was proposed by Bakadit at PPSN 2004 conference. This slide explains that idea. The training data are divided into several subsets. Then, in the first generation, one of those subsets is used for fitness evaluation. Then in the next generation, a different subset is used. And then another subset is used. At each generation, a different data subset is used. So the visual image of windowing a moving population in the huge training data. Here we have a population. Then the population is moving around in the environment. Then after enough iteration with the moving window, the population does not overfit to any particular training data subset because populations are moving around. And also the population may have high generalization ability. And now I'd like to explain our idea, parallel distributed implementation. Here we have non-parallel, non-distributed standard model of evolutionary computation. One population and one training data set. First, population is divided into multiple subpopulations, as in an island model. So here we have 5 subpopulations. Then the training data are also divided into multiple subsets. Here we have 5 training data subsets. This is the same idea as in the windowing method. Then an evolutionary algorithm is locally performed at each CPU. This is the same as in island model. Then the training data subsets are periodically rotated, for example, every 100 generations. And migration is also periodically performed to send a good individual to another island. Here, I'd like to explain the computational load of each of the 4 models. This is an original standard non-parallel model. Computational load is EC path plus fitness evaluation path. EC path is the selection, crossover, mutation, generation uplist. Those are genetic operations used for evaluation computation. Here we show the computational load of a standard parallel model. Fitness evaluation is performed in parallel. So computational load is equal to EC path plus fitness evaluation path. This path is 1/7 if we use 7 CPUs. Here we explain the windowing method. If we use a part of training data, the computation load is decreased. Here, in this slide, we use one of 7 subsets. So computation load is EC path plus fitness evaluation path. Here, we also, again, 1/7. However, in our model, EC path is also divided into 7 because we are using island model. So the EC path is 1/7, and the fitness evaluation path is 1/7. Now, I'd like to explain some result of computation experiment. We use this model. We have 7 CPUs, so the population was divided into 7 subpopulations. And training data were also divided into 7 subsets. And 7 CPUs and 7 data subsets. And each subpopulation has 30 individuals. So total population size is 210. For comparison, we use this model, standard non-parallel model, single CPU, single population of size 210, and whole data set. And we use a termination condition of 50,000 generations. Thus, in each population, we have 210 individuals. And that individuals were evolved for 50,000 generations. That's the total number of evaluations was more than 10 million evaluations, a lot of time. And we applied these two models, standard model and parallel distributed model. and computation load will be about 2%. So I examined, actually this deduction was achieved. Here we show 9 pattern collection programs from available data set. Some of them are many class program. Number of class is from 2 to 11. And number of attributes is from 5 to 40. And the number of patterns from about 2,000 to 20,000. Not big data, but not small data. This is the result about the computation time. Standard means standard implementation, A minutes. And our model means our parallelism model, B minutes. And percentage of B is B over A %. So the computation time was decreased for the first segment data to 2.3%. And next one, for NIM data, 3.0. And almost all of them are 2 point something. And some are 0.92. So we can say that the computation time was decreased to about 2%. Why? It's easy. The answer is easy because the population and the training data were divided into 7 subsets. So the computation load was decreased to about 2%. As a result, actual computation time was also decreased to about 2%. I also examined the test data accuracy using a 10-fold cross-validation, 3 times 10-fold cross-validation. Then we calculated the difference between standard result and our model result. And this slide shows the result. And the red font means improvement. And minus means the degrade of the test data accuracy. Out of the 9 data sets, we obtain an improvement for 6 data sets. Why? It's very difficult. But results show that our model improves the search ability of evolutionary computation. This slide shows the training data error rate over 50,000 generations. Still decreasing. So by increasing the number of generations, we may have a better result, and a much better result obtained from our parallelism model. But why did the model improve the searchability? This is because our model maintains the diversity. This slide shows the part of the evolution from 30,000 generations to 30,500 generations. Training data subsets were rotated every 100 generations. So that at each island, new data came every 100 generations. So the environment changes every 100 generations. So results show up and gradually down and changes at every 100 generations. And we can observe the range between best result and worst result. Best means the best. Oh, just the opposite. This is the error rate. So the worst means the best. The lowest is the best, and the highest is the worst. And the highest error rate is in a subpopulation, and lowest error rate in a subpopulation. So the difference means the diversity. But in the case of a standard model, the best equals the worst, so no diversity. This is maybe the reason why our model improves the searchability. We also examine the effect of training data rotation and dataset migration. In our competition experiment, we perform training data rotation and test rule set migration every 100 generations. And we also perform those rotation and migration in the opposite directions. And we also examine as a specification of data rotation interval and migration interval. In some computational experiment, we did not use data rotation or rule set migration. So no mean, no rotation, or no migration. And this is the errorless, the smaller the better. And here we obtain good result. If we use the rotation and migration in the same direction, here we have obtained good result and comparison. Opposite directions and same direction. Here we can observe interaction between rotation and migration. That is a negative effect of the interaction between rotation and migration. Now, I'd like to conclude my presentation. We explained the parallelism model. This is a parallelism model. And it was shown that the computation time was decreased to about 2% using 7 CPUs. Then it was shown that the test data accuracy was also improved. And we explained negative effect of the interaction between the training data rotation and rule set migration. And a little bit different model may be also possible for learning from locally located data subsets. In a model, data sets are rotated. However, if the data sets are locally fixed, for example, several universities have their own databases and they don't want to show those databases, we may be able to just ask to use those data for fitness evaluation. So in this case, subpopulations are rotated over different locations. Then we may be able to obtain a good rule-based system. And this idea can be also used for learning from changing databases. In a model, data are rotated so that at each island, environment are changing periodically. So I think that this model can be also used for learning from changing database. Image is something like this. Like this? Okay, that's all my presentation.
Thank you, Hisao. We have questions. You want to press there?
For the very last one, you said it could be used in a changing environment.
Yep.
Then you probably have to incorporate this so-called concept drift into it. Otherwise, when you rotate the data set from one to the other, the new learning, if you just treat it as a normal learning, will overwrite what you learned previously, causing so-called catastrophic forgetting.
Yes, thank you very much for your nice suggestion. I will try to do that in the future.
Any other questions?
I would like to ask, you split your test data sets into K parts.
Yep.
So you improve by 1 over K squared. So if in this example, you actually have split the data into 5 parts, you would have improved by 4%, right? So there must be some balance of the number of the partitions. There should be a trade-off how to choose this partition.
Yep. Yeah, right, yes. Yes, in some my primary computational experiments, I divided the data set into 49. We obtained a speed up, but accuracy was not good. So there are trade-off between high speed and high accuracy.
And how about if there are dependencies in the data? What if there are dependencies in the data
I see.
parts, then maybe we will not get the same thing as with the raw analysis.
First of all, this experiment totally depends on the hardware because seven CPUs are available for parallel computation. So we use 7 CPUs, and also the total data set were divided into 7. And we also examined this approach for very small data set, and the set of 200 or 300 or 400. In that case, it's clear that the data subdivisions did not work well. So that if you have a huge data set, I think that you can divide many. And if you have a very small data set, it's not a good idea to divide them. It's a natural, but not specific. But I think that there is a dependency on the data set. Thank you very much.